So to do that, we use the Sterling approximation. So this is something about the gamma function. Sterling approximation. Sterling approximation gives you the approximated value of the gamma. So you know that the gamma n, so that's you need to go through the Arfken and Weber, the book of the mathematical method for the physics, mathematical methods. So you can find the information about the gamma function. Gamma function. There are different edition of that, so I don't know exactly which chapter you need to look, but you can find it that the gamma function, even maybe some information in the chapter 1 or chapter 2, if there is something about gamma function. We need to go that, but how to write this expression when n is very big? So this is called, for that you needed advanced technique actually. Approximation expression of this series needed asymptotic to series expression. So anyway, by the thanks to this approximation, n factorial can be written like that, radical 2p n e minus n n power n, when n is very large. But to find this is very hard to find that actually. You needed to go to the Arfken and read the step to find this expression. You need a different mathematics. Even the complex variable function, maybe you can find it. Anyway, so this is what I want to say. So logarithm natural factorial will be radical of that. So it will be 1 over 2 ln 2p 1 over 2 ln n minus n plus n ln n. This is not very good. When n is very big. So let me to write this expression. When it is big, so this is just a number, so I can ignore that. So n plus 1 over 2 n minus n when n tends to infinity actually, or a very big number. So in comparison to the n, I can ignore the n, so n minus n. So I want to use, so you can use it as a quotient here. So this is your n actually. So instead of that, I can write it 3n over 2 minus 1 ln 3n minus 3n minus. Yeah. So with this, you can find the entropy. So entropy will be function of SNV. You can get also the energy from the expression of entropy, just make it the reverse. And that's all. So that was for the ideal gas. For the ideal gas, we do the calculation and quantum mechanical description actually. So there is a thing called Gibbs paradox here. The entropy, it should be extensive parameter. SNP should be extensive function of the extensive quantity. Quantity. So I mean that when you change a V to the alpha V and the N to alpha N, so and the E also, the entropy should change, Sn alpha N. That was the definition of the extensive element. That will be something like alpha, some number, Sn original form. In mathematical language, we call it S should be homogeneous function, homogeneous function of all the n. We don't know what is the n, so sometimes normally n is 2 or 1 even. Anyway, this entropy is not homogeneous, so this entropy is not extensive. And that caused the problem of the Gibbs paradox. You need to add one term to that, but you cannot get this term from the volume or something. This is the counting factor. So Gibbs paradox states that, of course, by considering two systems and writing the total entropy and something like that, you can read it in the text. So you can get that this entropy doesn't work as an extensive quantity for you. So you need a factor. This factor is a counting factor actually. 1 over n factorial. You needed that. You cannot find that. Why we need that? Before we study the next chapter, when we will talk about the particle distinguished and non-distinguished particles, some particle you can make a difference between them when you see them in the system, and sometimes you can distinguish particle and non-distinguished particle. Anyway, by this factor you can solve, you just added this factor by the hand to the omega. So if you replace it the omega e by the new omega e, just 1 over n factorial, the old one, the one which you find from the volume, you can remove the Gibbs paradox, but you need to go through the text and read it more about the Gibbs paradox. I don't want to spend the time here because we needed to explain that why this counting factor appeared. And we need to repeat that in the next chapter, so don't need it to make you confused more here about that. So this factor can solve all the problem and your entropy will be extensive. One thing remains from this chapter, from this topic, is that something about the homogeneous function. So because we will need that, so some mathematical preliminaries fact about homogeneous function. Of order, because we will need that later in the next chapters. So the physics part actually finished. So just a few minutes I will talk about the homogeneous function in mathematical physics. Actually in mathematics, basic mathematics. This is a called homogeneous function. If you have a function like that and satisfy this relation, we call it this homogeneous function of order n. So normally it shows some extensive quantity like entropy or something, and sometimes there is no any mean for that. Normally this is a Lagrangian in classical mechanics, or is entropy in statistical physics. No. Hamiltonian can be also, but Lagrangian or entropy should be an example of the homogeneous function. So generally speaking, if you have a function and this function is s at x1, x2, xn, and if you make it this alpha times just any coordinate, so if give you alpha f, s original function, that's we call it homogeneous function of the order f is an order. Okay, what do you understand from a homogeneous function? It's very important theorem. Theorem is for any homogeneous function of order f, you have this equation, sigma xi, partial derivative of that, we have f, so it will be very confusing. Let me to write this, the order I write g, okay. G f fx1. This is the proof is very easy, so you can prove that very easy. Just making the derivative with respect to xi, but take it that y1, y2, yn. So partial derivative of x with respect to the x1 will be partial derivative of s with respect to y1, on the y1, on the x1, will be alpha partial derivative of that with respect to that. This is from the left hand side, if I take the derivative of left. If I take the derivative of right hand side with respect to the, I don't need that. Now I want to just multiply this equation to the x1, okay? Just multiply. So it will be rx1 on the s1 the y1. So what is that? This is the y1. So y1 on the s1 the y1. Okay. It was better to take derivative with respect to the alpha first at all. So I want to take the first derivative of the alpha from this equation. So that's better proof, I think. But for that you needed to make a summation over that. So just make the alpha derivative from both sides. So run the partial derivative of alpha g, s, x1, x2, and x. This is the better proof. So what's given here? Partial derivative of with respect to the alpha will be partial derivative of that with respect to y1 and the y1 with respect to the run the s on the y1, run the y1, run the alpha plus again run the s y2, run the y2 on the alpha, and here just g alpha g minus 1, s x1 x2. Okay, what is the partial derivative of y1 with respect to this? This is the x1, x2. And what is the y1? Is alpha x1. This is the alpha x2. Can I just shift this alpha to the here? And here we have x1 run the s1 the x1, x2 run the s1 the x2. G alpha g minus 1 s. What's that? This is the alpha gs, and alpha gs from this is s gs. And what's here? This is a sigma xi on the g1 x. Sorry, yes. So this. A physical example is when we consider the Lagrangian. In classical mechanics, because we will need it that because we will use the Lagrangian in classical mechanics. Next chapter.
Just can you repeat how we get GS again after G?
Yes, because this is alpha GS. So alpha GS is
S.
yes, S because this is homogeneous function. Yes.
Oh.
Yes. This is a Lagrangian. So and we have a set of the coordinates like Q1, Q2. You know that this is a classical mechanics, you need to know. Okay, I want, and eventually the Lagrangian is the homogeneous function of the order 2. You know why? Because Lagrangian always appear like that. It appears like that, for example. Yes? We just keep it with common M. Minus potential of Q1, Q2. I removed the N here, time here. I don't need it. It's a time independent system. For that system, consider just this system. For this system, for many cases, Lagrangian is the homogeneous function of the order 2. So I mean, if I write alpha for example, like harmonic oscillator, I will get alpha squared of the original Lagrangian. For example, if you take this harmonic oscillator, 1 over k, Q1 squared, Q2 squared. At least for harmonic oscillator, it's correct. And for many class of the function, you can do. So Lagrangian is the homogeneous function of order 2. So immediately from this discussion, I can see that sigma Qi, run the L, run the Qi, you don't need it to write that because the homogeneous part comes just over the coordinate. So, and we suppose that the potential is homogeneous function, or even you can forget about the potential and just consider the kinetic term, like that. This is definitely homogeneous function, that's we don't know, but many cases I told you, many cases like harmonic oscillator, they are considered as a homogeneous function. At least for the kinetic. Well, this is the equation. So from this equation, you don't get anything zero. This is just a. But just I told you, just forget about the potential, or consider the potential very, very symmetric like that with a square. If you forget the potential, so the Lagrangian will be just kinetic energy, and you will get just q dot I, run the t, run the q dot I to L. There are many applications of that. For example, to derive the Hamiltonian from the system, sometimes we need this information. The Lagrangian should be homogeneous function of the second order to get the correct form of the Hamiltonian. Just I give you this example just to see that it really happened. So this is explicitly about the function which is given is homogeneous. Because if you make alpha, 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 it becomes alpha squared. So it's definitely homogeneous. With the potential to be homogeneous, without the potential to be homogeneous. Of course, not for all the case. The one that I want to add here is that you need to remember that from the classical mechanics, the P, the conjugate momentum corresponds to any coordinate is partial derivative of L with respect to QI. And then you have just a kinetic term, so that will be that. Yeah. Just. And look at that, this is what exactly appeared here. So can I write this expression? Q dot I, pay I to L. Okay? And look what I want to develop an interesting equation from here. Just. The interesting equation is that keep it this information just when you don't have any potential or something. So you have sigma q I pay dot to L. If I define the Hamiltonian like q dot pay minus L, I define that. This is the definition of Hamiltonian. At least for time-independent system we can use. And using the fact that, use this fact, so if you plugging star in this equation, we get, instead of the sigma pqi